Okay, we're going to do chapter 3. Chapter 3 is linear equations and inequalities. But specifically, we're going to start with the linear equations part. And in this case, 3.1, we're going to graph linear patterns. Okay, and then later on, we'll get into the other parts of the equations and inequalities. Okay, before we do 3.1, let's go back and briefly look at chapters 1 and chapters 2, because they all build on each other, not surprisingly. Okay, chapter 1 was using algebra to describe, and they used tables to describe, they used graphs, they used equivalent expressions and talked about whether or not they appeared to be equivalent or they weren't equivalent, and they used mean absolute deviation, which is a way to describe the spread of data. Okay, chapter 2 talked about algebra to explain, and the primary way they used algebra to explain was properties. Properties explain why things work, okay, including using properties to absolutely, positively prove that either two expressions are equivalent or absolutely, positively prove that they are not equivalent. And properties is the only way you can do it. Tables and graphs won't do it absolutely. Okay, so that said, you see how I have the colors here. Tables and graphs are part of chapter 1, and tables and graphs are coming back in chapter 3. Okay, equivalent expressions were in chapter 1 and chapter 2, and they're in chapter 3. And properties were in chapter 2, again in chapter 3. All these things, the tables, the graphs, the equivalent expressions, and the properties are being used to solve linear equations and inequalities. Okay? And then the last thing that is brandy new is this one, clearing fractions to solve linear equations and inequalities. But we'll get to them later on in chapter 3. All right, let's talk about 3.1. 3.1, the big idea is that you can have either constant increase or constant decrease situations, and those situations lead to linear graphs that create a straight line, and they are represented by something called a linear equation. Okay? Now, just so it's here where you can find it, here's the homework. Read 3.1. All right? Write down the one and only vocabulary word that's in 3.1. And then do 1 through 19 odd. Right. Now, constant increase. Let's say Miss Lovett's filling a pool. You know how she talks about this each year? She says, what would you fill a pool with if you could fill a pool with anything? Well, I know that Miss Lovett loves Twizzlers. Not red vines, but Twizzlers. And so she starts out and she goes down to the High Meadows pool and she puts 10 packages of Twizzlers in the High Meadows pool. Okay? Then the next day she goes down and she puts in 3 more packages of Twizzlers. And each day after carpool she walks down there and she throws in 3 more packages of Twizzlers. All right? After a certain number of days, you could figure out how many Twizzlers she's going to have, because her equation is 10 plus 3 for the number of days will give her the number of packages of Twizzlers. Okay? So P stands for the total packages, and D stands for the days. Okay? Now, 1 year has 365 days. So you could put 365 right there and figure out 365 times 3 plus 10. She's going to have a lot of Twizzlers after 1 year. 1,095 packages of Twizzlers. Okay? So here's the table that shows it, going from 10 to 13 to 16 to 19 to 1,095 packages of Twizzlers after a year. And here's the graph that shows the same thing. The graph doesn't go as far because it's hard to fit all that on one page, but it starts her out going with 0 days having 10 packages, 1 day having 13 packages, 2 days, 16, 3 days, 19. Okay, and it keeps going and going and going like that. All right, now, what's good about the graph versus the table versus the equation? The graph is a nice handy-dandy looking picture. You can see what's happening. That's real helpful. The table sometimes gives you a lot more details than it's able to see in the graph, especially if I wanted to go line after line after line after line after line. But the equation, the beauty of the equation is it can say, well, how about after 10 days? Hey, what if I said 365 days? What if I said 500 days? Okay, I don't have to keep creating a table line after line after line. I could just go right to the equation and figure it out. Okay, now that table created something, or that equation rather, created something called a constant increase. Okay, a constant increase is when something increases by the same amount in a period of time. Okay, now in a little while we're going to talk about a constant decrease, but a constant decrease is something that goes down by the same amount in a period of time. Whether it's a constant increase or a constant decrease, either of those things can be something called collinear. And again, that's your one and only vocabulary word in 3-1. Collinear means, well, first of all, co, like coexist, or co-owner, means that something's with something else, okay? And linear obviously means line. So on the same line is collinear, okay? Collinear, points that all lie on the same line. Now, you don't literally have to draw a line to be collinear. This situation where Miss Lovett's putting 3 packages of Twizzlers in the pool every day, even though they are not connected to one another in a line and they are a scatter plot, they are still a collinear graph because, you know, you could visually draw a line through them. Okay, constant decrease. Now Miss Lovett said, okay, fine, a year has passed. I have 1,095 packs of Twizzlers in the pool. She says, you know what, I'm going to start eating those Twizzlers. So they've got lots of preservatives in them, and she goes down, she says, I'm going to pull 2 packages of these Twizzlers out. Okay, so like on a Monday, she goes out and she eats 2 packages of her Twizzlers, and she's down to 1,093 packets of Twizzlers. On Tuesday, she goes down and she does it again, and she's down to 1,091 packages of Twizzlers. Then Wednesday, she's down to 1,089. She keeps doing this for a while, okay? Now she's like, wait a second. At some point, I'm going to get pretty low on Twizzlers. Let me figure out when I'm only going to have 100 packages of Twizzlers left. Well, that would be this equation. Starting with 1,095 and taking away 2 each day, where D stands for days, when will I equal 1,000 packages of Twizzlers? That would be her constant decrease equation. There's the table and here's the graph, but our graph doesn't go far enough to figure out how many days till be at 1,000. We have to use our equation for that. Okay, so using our equation, you'd say, how do I solve for this? I've got to get D all by itself. That's what I'm trying to figure out, okay? All right, when D equals 100, that's what I'm striving for, okay? So, the first thing I need to do, if I need to get D by itself, I need to get this guy to go away. And the way to get that guy to go away is to subtract 1,095 from both sides. If I subtract 1,095 from the left side, I'm left with that. And if I do it to the left side, I have to do the same thing to the right side. Okay? So now I have negative 2D is equal to 100 minus 1,095. Well, that means negative 2D is equal to a negative 995. Well, again, I still am trying to get to D, so I got to get rid of that negative 2D. Well, to get rid of negative 2D, you divide by negative 2. Okay, so I divide this side by negative 2, and I divide this side by negative 2. These two negative 2's cancel. That's kind of why we chose it, right? So now I'm left with D on the left-hand side. And then negative 995 over negative 2, those two negatives cancel each other and they become a positive, okay? And 995 divided by 2 is 497.5. So after 497 and a half days, she'll be down to 100. Now, we said that she's not taking them out on half days. So honestly, she'd have to wait till 498 days to be under 100. Alrighty, so that's a constant decrease. All right, last thing, finding your way around a graph. So let's say you said, well, I need to find out a whole lot of stuff about Miss Lovett and these Twizzlers. How many days would it be before she has 22 packs of Twizzlers? You come over here and you say, there's 22 packs of Twizzlers, okay? I go across until I get to the point, stop when I get to the dot, and then drop down. That's 4 days. 22 packs of Twizzlers, 4 days. Well, what if I wanted to go in the other direction? At a certain number of days, how many packages of Twizzlers will you have? Like, hey, what about at 6 days? At 6 days, hit my dot, go across. At 6 days, she's going to have 28 packages of Twizzlers. Okay, so that's how you'd read the graph. Couple last things to consider. When should you connect points and when shouldn't you? And we talked about this before. It depends on the situation, okay? Now, we don't have any half days here. It's not like she's standing there in front of the pool and throwing in a Twizzler at a time every second. So there are no points between here and here that make any sense. Plus, she's not thrown in an 11th pack and a 12th pack, or a 14th pack and a 15th pack, so there's no points in between here and here that make any sense. So we have to leave these as separate dots. Okay? Another thing to consider is the domain. Well, the domain has to do with your x-axis. That's what domain is. Domain is the numbers that make sense for x. X that makes sense. Okay? So in this case, the x that makes sense are positive integers. In this situation, it's positive integers because you can't have any negatives and you can't have any decimals or fractions. Okay? All right. Couple last things. In constant increase and constant decrease equations, it's very often that x-axis is often time and the y-axis is often something measurable. And that's pretty much it. Okay?